In this video, we'll start discussing functions of several variables, and let me start with the two-variable case. So let's talk about functions of two variables. And as you can probably guess, what happens is you get a rule that a function that assigns ordered pairs of real numbers to real numbers, which are the values of the function. So to give you an example, f could be taking x and y as input, so this pair x and y, and give you as the output the square root of 9 minus x squared minus y squared. So this is a function of two variables, and your basic notions of a domain or range of functions that you are used to from the single variable case nicely generalize to this case as well. So the domain of a function is the set of all possible xy pairs. So think of what it means in the case of this example. So what kind of allowed pairs of x and y we can have in there. So pause the video and select your answer below. Okay, I hope you paused it. So the only restriction that we have on the xy pair is to get something that's non-negative under the square root. So that's equivalent to saying that the squared sum of x and y should be less than or equal to 9. So this is a disk, a closed disk of radius 3, centered at the origin. Okay, so that's the domain, and the same goes for the range, as I said. So the range can be nicely generalized, and the range of the function is the all possible values that the function can take as the input values go and vary over the domain of the function. So the range of f in this example, well, think about what kind of values it can take and input your answer below. Okay, I hope you paused the video and realized that as you go from the boundary of that domain, of that disk, there, when you have this equality, you get 9 minus 9, so the value is going to be 0. And as you go all the way to the origin, you increase the value of the function all the way up to 9 minus 0 when you are at the origin, where you get root 9, that is 3 for the value of the function. So the range of this function is the closed interval between 0 and 3. So this is for the domain and the range, and the notion of the graph of the function can be also generalized to this case. So let me just show you the graph of this function. It looks like this, like some cap, which has this nice rotational symmetry, and you can see that circle of radius 3 at the boundary, and you can also see that it takes its minimum values there. Then as you go and move towards the origin, you reach the maximum of that function. So let me just try to put this in the usual x, y, and z coordinate system. So that this surface would be the graph of our function. So this is the graph of root 9 minus x squared minus y squared. Okay, so the notion of the graph also generalizes, but instead of a curve, in this case, we get a surface. Okay, so one more thing that's a new notion is the notion of level curves or contour maps. So the level curves you get by slicing through the graph of the function with planes parallel to the xy plane at different heights. So the level curves are defined for all values k from the range of the function, all possible values that the function can take, it consists of those xy pairs for a fixed value of k, for which f of x and y is equal to k. Okay, so that's the level curve corresponding to the value k, and this can be considered for all k from the range of the function f. In this case, in this example, for all numbers between 0 and 3. And to show you, this is what the level curves or the contour map of this function looks like. It's concentric circles around the origin, with C0 being the boundary circle of radius 3, and C3 being the innermost circle, which is actually just a point, the origin, at which the function takes the value 3. Okay, so you can think of these contour maps as these topographic maps of mountains, where you have these different lines of elevation, and this is level curves for you, which is a new notion in this topic. All right, I hope you enjoyed this video, and I'll see you in the next one.